we'll turn around so that we're facing the western horizon instead of the eastern. High in the sky to the west, we find a pair of stars with twin lines of fainter stars coming off of them. I'll put up an outline so that we can see Gemini, the twins. They form mirror images of each other in the sky. I'll put up our artwork as well. In Greek and Roman mythology, the twins were named Castor and Pollux. And those are also the names of the two bright stars that we see at the head of the twins. The so-called twins were technically half-brothers that were such inseparable friends on Earth that they wanted to be immortalized side by side in the sky. At the foot of Castor, we'll find a bright red dot. Not a star, but a planet. The planet Mars. Mars is the red planet named for the Roman god of war. It won't always be in this spot by the foot of Gemini. The planets all move around in the sky. We find them in different places from month to month and year to year. The planets are all going around the sun just like we do. We're going to take a closer look at Mars by zooming in on it, kind of like we did for M87. Here we see a zoomed-in view of the planet Mars, our neighboring planet. It's smaller than Earth, only about half as wide, and it gets this red color because the rocks on Mars have a lot of iron in them. Iron oxides, it's kind of like Mars has rusted. The most recent NASA mission to Mars is a rover called Perseverance, and it successfully landed on February 18th this year. It touched down in a spot that we can actually see near the top of Mars right now in our view. It's near the edge of a dark region, and it's a crater called Jezrow Crater. Now, Perseverance is going to drive around that crater, investigating signs of Mars's watery past. The crater appears to contain a dried river delta. It'll look for signs of possible past life on Mars as well, and test new technologies that could become staples of future Mars missions. One of the most exciting tests of brand new technology is a helicopter drone. Let's take a look at that drone. This was called Ingenuity. Now, Ingenuity was successfully unfolded from Perseverance, from the rover, and then it was left on the Martian surface. And this is the photo that Perseverance took of it on April 5th. So this was very recent. Even robots struggle to survive on Mars through frigid nights that can plummet to negative 130 degrees Fahrenheit. Ingenuity has so far weathered its time on Mars. Let's take a look at some tests of the blades turning. This was a slow spin test. Now, they had some trouble with their fast spin test of the blades, but the Ingenuity team did some troubleshooting, and they were able to work out the difficulties and actually did their first successful flight on another planet, on the planet Mars, in the morning on April 19th. Ingenuity here lifted up off the ground about 3 meters successfully and then came back down. This is an incredible feat to fly on another planet, especially Mars having a very thin atmosphere compared to our own. It's only 1% the thickness of Earth's atmosphere. This was a historic flight. Let's take a look at the first photo that Ingenuity sent back from above the surface of Mars. Flying only meters above the ground, we're seeing here the shadow of the Ingenuity drone. We'll zoom away from Mars and look for another object. Another NASA mission is active around a different planet, the Juno mission to Jupiter. Jupiter's not up currently in the evening sky just after sunset, but you can find it in the morning sky to the east just before the sun rises. Let's fly to Jupiter, traveling over the Earth and going to the morning sky first. Lifting off from North Georgia. We can see some sunlight there, but that's actually the setting sun. Instead, we'll travel over the north pole of the Earth to the other side of the planet, where we're then seeing the morning sky, sunrise. We'll head out to Jupiter, traveling hundreds of millions of miles through space. And as we get closer to Jupiter, you'll see a sort of blue structure around it. I'm showing the magnetosphere of Jupiter. These are magnetic fields generated inside the planet. They form a sort of cage around Jupiter. Those magnetic fields are the strongest of any planet in the solar system, and mapping them was the main goal of the Juno mission. It got to Jupiter in 2016, and the original mission was meant to wrap up this year in 2021, but NASA announced that they're going to extend the mission through 2025. What Juno does is it goes on orbits around Jupiter, polar orbits that sweep over the north and south poles of the planets, and also brings it very close into Jupiter, only a few thousand miles above the cloud tops, and then swings out far, over 5 million miles away from the planet, so that we can map those extensive magnetic fields. Close up, we're seeing this gas giant planet. It's made mostly out of hydrogen and helium gas. The colorful bands we see are trace amounts of other elements and molecules, things like ammonia and water vapor. The magnetic fields of Jupiter would normally be invisible to our eyes, but mapping them with Juno is telling us about the internal structure. It's telling us about what Jupiter is like under the cloud tops, where we can't see. The magnetic fields also play a big role in channeling charged particles around Jupiter. These are things that come from the sun. The sun gives off a solar wind, particles that fly through space, and they hit Jupiter's magnetic fields, and they can be channeled towards the poles. Jupiter also has a very volcanically active moon called Io that gives off charged particles too. And all of these particles are channeled towards the poles where they start to glow. We call this an aurora. Here on Earth, we see auroras caused by Earth's magnetic fields, channeling charged particles down towards our poles, causing the northern and southern lights. Let's take a look at a photo of some of Earth's auroras. This photo is taken by the International Space Station, so basically a picture from low Earth orbit of auroras over Canada. Now, scientists are finding more similarities than expected between Jupiter and Earth's auroras. Bursts of brighter, thicker auroras on Earth that happen in the dead of night are called substorms, and they start as small beads and then expand. We'll put up a model of Jupiter's auroras that go over the poles. Now, from Earth, we've taken pictures of these auroras with the Hubble Space Telescope in orbit around the Earth, but it can only see the bright day side of Jupiter. What we've often noticed are called dawn storms, auroras lasting about 45 minutes long, bursts of them on Jupiter. Now, Juno goes over the poles of Jupiter, and so it gets a full view of the auroras, including the day and night portions of the auroras. Let's take a look at some pictures from a study that just came out this year that looked at the auroras with the Juno satellite. And these pictures that you see here are taken in ultraviolet light. So that's a little bit higher energy than what we see with our eyes. What they found is that the dawn storms are not accurately named. They begin around midnight on the darker side of Jupiter, as you see in the picture here on the far left. Now, that's the side facing away from the sun. And what we see there is small beads that start to form, and then as it comes to the picture on the far right, we're seeing that they expand, and eventually they'll swing out to the day side of Jupiter and form what we see as the dawn storms. But they're actually lasting 5 to 10 hours long and beginning in the night side. Now, on Jupiter, they're rotating with the giant planet into the daylight, but they basically behave exactly like the substorms we see for auroras on Earth. The only difference is that on Earth, the auroras stay in the night side of our planet. They don't really swing out to face the sun. They're staying facing away from the sun. Understanding the differences between Jupiter and Earth's auroras and our magnetic fields can tell us a lot about our planets, but also what they share in common. And studying these planets close up can reveal the wondrous effects.